you may still ask, right, what indeed does this time constant mean? So let's just dive a little deeper at this time constant thing. This capital T, what does it mean? Okay. So let's look again at this transient curve. Right? And let's assume for a second that the transient of the response will behave always follow the first derivative, the initial slope of the curve until it reaches the steady state level 1. And let's try to find out how much time it takes. If it doesn't slow down, if you look at the curve at the beginning it's fast, right? But gradually the speed will decrease and eventually basically will have very, very small, or this diminishing returns curve, right? The change becomes smaller and smaller and smaller and smaller. Eventually it basically becomes flat. But if you can maintain the initial slope, initial increase rate, how much time does it take to reach the steady state level? Let's do a simple calculation. So the question we're asking is, what if y of t, your response, increases or would increase by its initial slope? And never slows down. Okay, this is the question we're trying to ask. Now, the response curve 1 minus e to the negative t over t, right? Take the derivative with respect to t such that you can find initial slope. You take derivative, so 1 with respect to t will be 0. An exponential will be itself. So you have a minus sign here, you have a minus sign here, you have no minus signs, and you have this 1 over t, so you have 1 over t times e to the minus t over t. And initial slope will be derivative of the curve at time 0. So if you plug in t equal to 0, apparently it's going to be 1 over t. So if you are always increasing with this rate, how long does it take to reach the steady state level? Apparently it takes your target is 1, our speed is 1 over t, so 1 divided by 1 over t is t to reach your steady state, which is 1 in this case. Or now we don't need this question mark anymore, right? You can simply say, well, I figured it out, it's going to be capital T. And this is, again, your time constant, right? So what does the time constant mean? If you increase or change with your initial slope, as soon as your switch is turned on, it takes 1 time slot to reach a steady state. But since you have this dynamic built into that because this Ts plus 1 term, it's going to take roughly 4 time constant to reach the steady state. That's your set one time. Okay. Now, all these discussions, of course, if you go all the way up at the beginning of this section, we assume that DC gain is equal to 1, right? That's right. here. But these results, okay, settling time, rise time, they're independent of DC gains. So I want to point out that these results above remain valid for first order systems with non-unity DC gain. Okay? All depends on your time constant, as long as you calculate your time constant correctly, or just simply follow all the math procedures, you should be able to find the correct results. But on the other hand, when you talk about 4 time constant being the settling time, it applies to all first order systems, as long as their asymptotically stable. And if you say the rise time is about 2.2 time constant, it's going to be true for all first order systems, again, as long as the systems are asymptotically stable. So this is the story for first order systems. And let's just, for this week, start the discussion of second order systems, which will be a very important topic, and we'll spend probably next week on this, maybe 1 or 2 lectures as well. But let's just begin some of the discussions, some of the discussion of some of the simple cases. So we're going to look at second order systems now. And we're going to focus first on systems with no zeros. No zeros means if we'll look at the transfer function, the transfer function only has a constant term in the numerator, nothing else. Input is still going to be our unit step signal 1 over s being the Laplace transform, output y of s. And again, I construct my transfer function of the system such that, again, as you can see, the DC gain is equal to 0. But as above, the results we discussed are going to be applicable to non-unity DC gain systems as well. So this doesn't introduce any specific scenarios by letting the DC gain equal to 1. Now, of course, it's a second order system, right? So we should have 2 characteristic roots. And let them be lambda 1, lambda 2. Okay. They could be defined by your capacitors or inductors in combination with the resistor in a circuit, for instance. And as we mentioned, and as you can find out maybe from your high school algebra notes or maybe your calculus notes, that when you have a quadratic equation, the sum of the 2 roots will be equal to negative a. Okay. Product of the 2 roots will be equal to b. Okay. And of course, lambda 1 and lambda 2 will be equal to, in this particular quadratic equation, okay, equal to this. Alright? And of course, in the square root, it can be, real numbers, they can be complex numbers. We didn't really have to say they are real numbers. They can be complex as well, but they both will take this form. Okay. So what else can be done? Now, if we look at the characteristic roots, right? apparently what we can do is, well, now the output signal can be written as the Laplace transform of your input, and then I have s minus lambda 1, s minus lambda 2. That's my denominator. Your numerator is b, and b, as we have done here, will be the product of the two lambdas. The product of their two lambdas. Okay. And this is because we make the DC gain equal to 0. So if you look at even in this form, you can find the DC gain equal to 1. Sorry, the DC gain is to be set to 1. And the cover-up method still applies, so you can possibly calculate again what will be the building block signals. Right? So if plugging S equal to 0, basically there's a DC gain, so DC gain equal to 1. So in the steady state, you should see a unity in the steady state. So that's your 1 over S. And you have two first order terms that will give you two exponential signals, S minus lambda 1 and S minus lambda 2. Using the cover up method, it's possible to find out that one of them will be lambda 2, lambda 1 minus lambda 2. The other will be lambda 1 over lambda 2 minus lambda 1. It's not difficult, to find out this by using the cover-up method. And you can then do the partial fraction expansion is done. You can do the inverse Laplace transform. So again, for t greater than 0, 1 over s is your unit step, so we just write 1 since it's positive time. And then lambda 2 over lambda 1 minus lambda 2 times e to the lambda 1t plus the other exponential term. And the way we can write it into two separate exponential terms is we also assume that lambda 1 is not equal to lambda 2. So you don't have repeated roots. If they're repeated, they would take a slightly different form. But if they're not repeated, okay, it's possible to write these two separate exponential terms. So non-repeated. Okay. So this is the time response of a second order system in the mathematical form, assuming the two roots are not repeated. Okay. Then of course we should really think about and understand, right, given this mathematical form, what it should look like. What does the transient response looks like as a function of time, right? Like in the first order system, we can draw this curve easily, just have one exponential term. When you have two exponential terms interacting with each other along with that constant 1, how does the response look like? And there are usually 4 cases. Okay? Well, first define these 4 cases, and then next week we'll go into each of the 4 cases. So the first case will be when both of them are real and both of them negative. Okay, so in this case, both exponential terms will be decaying over time. And when you combine them together, apparently the steady state will be 1 since the DC gain will be 1. And they have two exponentially decaying functions aggregated together. the behavior of the transient will still look like this monotonic increasing curve, similar to the first order case, only you have two exponential functions added together instead of one. In this case is what we call the over damped case. When both roots are real, both are negative, you only have exponential decay. Second is when both are complex. Both of them all have imaginary parts, and because they are the roots of a quadratic equation, when both of them are complex, they're actually complex conjugates. So both of them will have the same real part. Usual, so we'll have all the real part. Both roots have the real part being negative. Now, when you have a complex, right, e to the lambda t, when this lambda is a complex number, and we discussed this at the signal will behave as the combination of exponential decay and the sinusoidal oscillation. The decay is defined by the real part of the exponential signal, and the oscillation defined by the imaginary part of the function. Okay. You have a decaying oscillation, eventually goes to their steady state, which is 1 since DC gain is 1 again. This is what we call the underdamped case. The underdamped case. Underdamped apparently means the damping is not strong enough such that you can go over the steady state level and have this overshoot. Now, third case is a little bit special. We're assuming both lambda 1 and lambda 2 are pure imaginary. That means, well, this case actually implies the system is not asymptotically stable, but marginally stable. This is a special case, but usually we don't really run into asymptotically. We don't really discuss marginal stable system. We want to focus on asymptotically stable systems, but for second order systems, since this is really representative of a particular scenario, we want to also have this in the discussion. And if lambdas are pure imaginary numbers, then e to the lambda t, they will be just sinusoidals. And for the output, that's what you will see. You see sinusoidal output. Okay? Sinusoidal output. This is sometimes called the end-damped case. And there's no damping at all. Just the oscillation will remain and have the same amplitude forever. Okay, that's the third case. And the last case that we didn't really, and both real and repeated. When they're repeated and you want the system to be stable, they must both have a negative real part. So just refresh your memory of 3101, how to determine the stability of linear time invariant system. Now, in terms of the behavior, it's very similar to the overdamped case. Still look like this. Okay. But usually the transient can be a little bit shorter. I'll discuss when we have the formulas why this may becomes a little bit shorter. And this is called a critically damped case. Okay. So for stability behavior depending on how the transient are presented, lambda 1 not equal to lambda 2. So overdamped case, overdamped case, underdamped case, damped case. All four of them are qualitative different from each other. And what we'll do in chapter 4 is we'll study each one of them. We'll focus mostly on the overdamped case and the underdamped case since they are more representative. Okay. We'll discuss several issues, how to calculate all the performance measures, and also how we can extend this discussion to more complicated systems like third order systems, fourth order systems, higher order systems, and so on and so forth. And that will be the goal of this chapter. Okay. And this is the end of this lecture that we want to cover on Thursday, September 20th. I'll see all of you next week in class.